That was an engaging talk. I really wanted to listen to you more. But however, I'll start with the questions. We have a lot of questions from the audience. So I'll collate the questions and bring them up to you. So the first question is, when it comes to UV photo cleavage, what wavelength tends to be the most effective, and does that vary significantly depending on the material of the cleavable chemistry involved? Like whether the material or the cleavable chemistry.
I think that UV will have a strong damage to the conjugate polymer. That's been known to the field for many years. That cleavable linker. So let me put it this way. So if you try to destroy your polymer, the best way is using UV. But whether the intensity, the wavelength, the dosage you're using to cleave a side chain, cleave the functionality depending upon which chemistry you're using. So this is actually a very good question, because I think there are better ways to using photo to cleave if you can design the very benign, say maybe red light, to create a very low dosage to cleave the side chain. I think that would be much better than having UV, because you do not want to touch the backbone. Otherwise, you're losing all the optoelectronic properties you have in the first place. Yeah, that's a very good question. I think very much worth researching.
So I'll go to the next question. Can the concept of cleavable side chains be used to design conductive material capable of shape recovery upon exposure to external stimulus?
Can you repeat? I did not quite get it.
Yeah, so they want to know if we can design a conductive material that is capable of shape recovery upon providing external stimulation.
That's a really good question. I haven't thought about that, but yes, that's possible, because if you again, that's depending on how you design the material. One thing I can think of is that you can try to build a classic conjugated unit into the chip memory design. So you can still maintain that chip memory having different TGs, and then the conducting polymer can still give you the either coloring or maybe the conductivity. The other thing which could be more interesting is to using the changing nature of the TG of the conjugated polymer, using them as an element to create this shape memory. So that would be more interesting, but I haven't been able to think about what is the best way. But that's a very good idea, though.
Thank you. So the next question is, can melamine-based polymers be used as dopant to increase conductivity? And also, how about exploring bio or enzyme-mediated approaches for cleaving side chains? And yeah, so are there possibilities for sonochemistry, mechanochemistry? These are the types of questions they want to know about how we can go around cleaving the side chains.
That's a beautiful question too. So imagine that if you have a conjugate polymer decorated with sugar, right? So like polysaccharide, you can make them in water soluble. So now you put in a water solution, put some enzyme, and then it's going to eat the sugar off, and your conjugate polymer will be becoming precipitate. That's possible. And I think a lot of the chemistries are not being used yet. It's just simply because we have not been able to justify them. So if you had the need to use enzyme and sugar, say in your body and for some other reasons, absolutely. So so I think that what I was talking earlier today was just some snapshots of what we can do. Very often that you marry different chemistry to the conjugate polymer, depending upon your application, you will be able to come with some new ideas. So to your earlier question, that yes, you can use a polymer as a dopant, and in fact that you can use a P and N type polymer, creating a very interesting interchangeable doping. So that has been done by Fabiano in Sweden a couple of years ago.
Yeah, thank you. So I'll jump to the next questions very fast, provided the time. So in a scale-up scenario, provided that the side chains make up 50% of the polymer mass, so what do you see as the, whether to use cleavable side chains are a route to be cleaving the side chains could be, a good way of sustainable use for raw materials. So I'll reframe the questions once again. So the thing is, if this kind of chemistry can be used to improve the sustainability of raw material use, and in a scale-up scenario, if it can reduce the cost for resource intensity of manufacturing.
Yeah, so let me try to take what I said earlier back is there are ways you can process the conjugate polymer without the side chain. So one thing you could do is you creating these essentially dispersion or maybe some of the nanoparticle based, surfactant based nanoparticle dispersion or suspension that you can process them. This has been done in the field for a long time as well. When we talk of processing, we talk about the molecularly dispersed or dissolved into the solvent. So that will allow you to control the morphology once you've done the processing, and depending on how you process, you can even create the liquid crystals or things like that. In that situation, yes, we do need the side chains. And I think that, yeah, so that's where we are. But I'm not saying that side chain is absolutely necessary for processing purpose. We have to give you a context before we can answer the question in the proper way.
Sure, thank you. So another question on computational chemistry. How can this be very useful for guiding polymer design when it comes to better packing, charge transport, and stability?
Great question. So I think that in that case, if you try to enjoy the side chain free and also the high mobility connectivity, everything you wanted to have the conjugate polymer, you possibly need to spend some time on the processing, because if you simply remove the side chain, let this polymer freely oriented in any way they like, you possibly won't able to have a guided packing. That's what you need for the high mobility and the connectivity. So one thing I was thinking is that you could potentially do the guided process, which means that you process them into the well-packed, aggregated state for the optoelectronic application. At the same time, you remove the side chain, so that will lock in the process of the film. That would be what I call guided processing while you're removing side chain. So that would be the ideal situation. But I haven't really figured out what is the best way. Maybe you're doing the processing. If you had like gentle heating, it's gonna lock in the morphology. But again, you need some sort of the lower temperature processing, because any high temperature, your material will gain much more energy to be activated. You can move anywhere. Then you lost the packing already.
Thank you, Professor Yu. Last question. So this would be what do you see as the most promising direction for advancing cleavable side chain strategies? Like, do you anticipate breakthroughs more in molecular designing or processing methods or device integration?
That's a beautiful question. So I think that depending on your end goal, right? So one earlier, the question was about the thermal, shaping, the shape memory. So if that's your application, then you can definitely use the concepts of the cleavable side chain tunable TG to allow that happen. And if your goal is to having something like you can use for your, iPhone display, and then I think that your goal would be like, I want to be able to have the highest chromophore density. I don't want to have anything insulating. Then back to my earlier point is it's about how you process. You want to be able to process in a way that either small molecule polymer maintain that closer packing, even synergistically using processing and the side chain cleavage to achieve something you can't even do with the thermal evaporation. That would be ideal. I think that's definitely doable because there are many parameters, and especially now you have AI helping you identify what is the best processing. So it's possible. We just haven't been able to exhaustively try everything we could think of. But again, that's a very good question. I definitely think it's going to be happening down the road. You want to have the low cost of processing as a solution processing, but you also want to be able to have a high performance, which you get from thermal evaporation. So that's where the tension is. That's where you can spend the time to ease the barrier.
Yeah, sounds good. So we have a very inquisitive audience asking too many questions, but due to the time constraints, we'll be closing it here. Any final remarks or parting thoughts for the young researchers here who want to work on cleavable side chains and conjugated polymers?
Thank you.
So would you like to share any parting thoughts for these?
Yeah. Sorry about that. Yeah, I think being honest, I was inspired by a number of the questions the audience asked. I think that, particularly sticking to me is the shift memory idea. So, and the processing without sacrificing performance. So if anything, I want to be able to share with you, I think from a chemistry standpoint, again, you want to be able to create a new chemistry that would be allowing you to have almost the simple processing, side chain free afterwards, and minimal impact to the field morphology. All these things we need for the cleavable side chain. But on the other hand, I also want folks to be able creatively think about how we can strategically use the knowing chemistry to remove the side chains for new applications. I think that's going to be another very fertile playground where you can come up with some novel ideas and novel applications as well. Because traditionally, you want to be able to remove the side chain without sacrificing performance. That's why we came up with the cleavable side chain conjugate polymer. But it doesn't mean that has to be the only application. So I think, shift memory idea, the audience came up, and that was a beautiful idea. So there are many ways we can take this field to the next level. That's not just my effort; it's also hopefully being the community's efforts as well.
Thank you, Professor Yu, for addressing all these questions patiently. And thanks to the audience as well for such an engaging discussion. This was an insightful session, and we truly appreciate your time for the day. And now I'll pass it on to Neha for the next session.